nice to get a hand before the talk, right? Because I don't know if I'll get it after. Okay. I'll talk about the internet, the way I see that it's going, and I'll just get started here, right? While people are getting settled. So first, a little bit about me. Just the standard stuff. Master of Science from ITU, which is this university here. I've worked with Java since 1999, and I work as an independent developer or architect, and very often via the main sponsor or the big sponsor here, Lund & Bentzen, which is a consulting company here in Denmark. And I've been writing a lot, around 900 articles, and I have them on my website on this tutorials, jenkov.com. Maybe some of you have stopped by there from time to time. I know it has had about 75 million page views in its lifetime, so there's a chance that some of you have been stopped by. I'm also, when I'm not trying to pay my bills, being a freelancer, I am also working on a little startup where I'm a co-founder and also architect. My focus is on high performance distributed data and data science and these kind of things. From a bottom-up perspective, meaning I am moving from the infrastructure up. So I'm not an expert in AI, but my focus is on getting the data to the AI, and so that's my focus. Okay, so this is old stuff for all of you. We got Web 1.0 and 2.0, and Java was invented in this era of Web 1.0, and that means that Java was very much like when we got Java EE. Java was very much targeted at web applications running on the web, and that means that as the web fits very well with enterprise or with enterprise integration, the way it looked at the time, that meant that the whole Java ecosystem today has become king of enterprise integration. And that was very good. It was very good for Java in the beginning. But one of the problems that I see with that is that we also got stuck in that world a little bit, right? At some point, some of you have probably seen these predictions that we would get semantic web and intelligent web, and that never really happened. This was just a lot of talk. What happened instead was that if you take a step back and instead of looking at the internet as the web, but look at it as the internet, what happened was that the web actually just became another small part of the total internet. If you take a step back, we had the Wild West internet with Gopher protocols and FTP and all these kind of things, SMTP. We still have some of that, but it's not used that much. We're trying to standardize everything on the web with the REST interfaces and everything. But what has happened in the meantime is we got the internet of mobile apps, and while a mobile app can communicate with a backend through HTTP, it doesn't have to. And it most certainly does not have to have a web front end. Then we're getting the Internet of Things, and we're getting the Internet of Money. And these are all developments that are happening outside of the web. So as a Java developer, we're kind of being sidetracked a little bit by this development here. Because Java and the whole Java EE platform is still very much focused on enterprise integration, and we're still kind of stuck in web land. So, and let me just dive a little bit into this. What is it actually these new types of internet are consisting of? What is a thing? I mean, it's a little bit abstract just to talk about the Internet of Things, but if you have some kind of sensor sitting somewhere, it's usually either providing a service or it's provides data, right? So if you have a camera somewhere, either it's sending a constant stream of data to a backend, like a constant stream of photos, or it provides the service that you can ask it to take a photo at a certain time, or like now, or so that's really what the Internet of Things is typically data or services. And if we look at the Internet like that, we can go back here, then instead of the Internet of Things, we can say it's the Internet of data and services. Then, well, services we kind of already knew from REST services, but the Internet of Data is something which is new, or it's coming. So I could have supplemented that down here in one of the blue boxes with the Internet of Data, but that's what's coming here. So this is the Internet that is coming. Some of it is already here. I mean, cryptocurrencies have been here for quite a while, but for now, this whole technology is still very much limited to money. So cryptocurrencies, but like projects like Ethereum and these other similar projects are trying to expand beyond that and use the blockchain for a whole lot of things that we are today using standard web technologies for, like for instance distributed storage and like these kind of distributed contracts and everything. And then at the other end we have the Internet of Things, which I believe will lead to the Internet of Data. And one of the things that will come out of that is that I believe we will see the separation of data and applications, which means that today if you have data that you want someone to see, you can, of course, you can put it on a web server somewhere, but if you want somebody to actually see it, you would normally have to provide some kind of web application that shows the data or analyzes it in some way. And I believe that is going to change, so that in the future you will have applications that can analyze a wide variety of standard data, and you just need to provide the data. So if you're a researcher sitting somewhere and you're collecting data from for your project, then instead of having to import it into something like Excel and like fiddle a lot with it, you just kind of, you know, this is a standard type of data. You put it into an application, you will see it all in there. So these are some of the things that I think will happen. And then I think that is what will lead to what was promised with the web, the semantic internet. And we will need to get semantic data and semantic protocols. We will also get the intelligent internet probably after that. A lot of the way AI works today and machine learning works today is that it is working on massive amounts of data and learning from that. So once we get the Internet of Data, the internet, the intelligent internet is not very far behind, I think. And by semantic data and semantic internet, I actually mean machine understandable data and machine understandable internet. AI is already pretty good at extracting meaning from text, but if we can standardize how we format the data out there so it's easier to understand for computers, then it will be a lot easier for AI to analyze it, for machine learning algorithms to analyze it. Okay, so I think the Internet of Data is also coming to your enterprise systems at some point. If you look at the way old school SOA systems work today, you have this enterprise service bus, and you connect all your services, microservices or whatever, to that, and then they can contact each other through that. You can also have a model where you can have more direct service-to-service communication if you want to, but this is a very common model. This fits very well with the web paradigm. So for us Java developers, this is a very natural way of designing a system. But what is happening now is that we are replacing the enterprise service bus with an enterprise data bus. And so instead of in the microservice paradigm, one of the key rules there is that the service owns the data. So a microservice owns its own data. We're changing that. We're putting the data from the systems out on this enterprise data bus, and everyone who wants to look at that data and build up their own models from that can do that. So microservices no longer own their own data in the same way they do in the old web world. So I'm actually working right now for a big company that is trying to do exactly this. Take all the data out of all the existing systems, put them on Kafka topics, and share it with the rest of the systems in the enterprise architecture. And whether we will succeed with that or not, is still a little bit early to say, but I mean, this is how LinkedIn is doing it internally. This is how a lot of big companies in the US are starting to design their internal systems. So just as we were getting used to the microservice paradigm, we might be about to actually leave it behind again, or at least fundamentally change how we think about microservices. Okay, so this was a little bit quick. That is actually one of the things with this talk. As I was preparing it, I realized that it would either be like a 30-minute talk or like a 4-hour talk, and that is because it's either I could go into a lot of details about all of these things, and it would take a lot of time, or I would have to like go through it in a slightly more superficial way, and in that case, it might be a little bit difficult to fill out all 50 minutes. So we will see how far we get on and how much time we spend. Okay, so so what does that mean for us as Java developers? That a lot of the innovation that is happening outside of the area of the web. I mean, of course, we're getting new JavaScript frameworks all the time. We're getting new microprofile and new Spring Boot 2.0, whatever. But a lot of the big innovations are happening outside of that space. And so what does that mean for us? It means that this is something that I think we need to think about, both as individuals, and I think we need to think about it as a Java community. Because we risk getting left behind, because Java is still very much focused on enterprise integration. I mean, Kafka is one of the big steps ahead. It's not web, it is still enterprise integration. But it's one of the big steps ahead where we can maybe get a little bit back in track. I mean, it's no secret that if you worked in Java for a while, that Java is no longer the cool kid on the block. Right? And if you look around just at this conference, a lot of us are 35, 40 plus, and the cool kids go to the web and to other conferences. Either they are at the Ethereum conferences, they are at the Internet of Things conferences, there are a lot of other places. So this is something I think we need to think about. As an individual, you need to think about, do you really want to stay working in the enterprise integration world and risk getting left behind? I think as a community, we need to think about, can we do something that can push Java out of this enterprise integration bubble and maybe out into these new use cases where it could become cool again. And that is what we have done in Nanosai, which is the little startup that I'm working on the side when I'm not out paying, earning money to pay my bills. And so what we have done in Nanosai is we've built a little data intelligence. We are building a little data intelligence ecosystem. And so it consists of a couple of different things. Like we have actually we started with like the infrastructure for like a new platform, because we realized in the beginning we wanted to kind of look at the internet from the beginning. And if you need to take a step back from the web, you realize also that it's actually useful to take a step back from Java EE, because Java E is very much tied to HTTP. And once we started getting into that, we realized how much that protocol actually has dictated. HTTP has dictated of the design of Java E. It's quite a lot. Like, just imagine what would Java E had looked like if HTTP had been an asynchronous protocol instead of a synchronous request response protocol. Would we have had servlets? Probably not. We would have had something else. It might have looked a little bit similar, but the whole idea that you have a service method that takes an HTTP request and has an HTTP response where you can write the response back immediately is something that is dictated from HTTP, from the protocol. So we took a step back and said, if we have to look at this whole area again, and we have to create something that fits the like a new internet paradigm, we need to start with the protocols. So that's what we did. We started designing a new protocol instead of HTTP. We call it IAP, and for that we created a binary data format called IAM. And then we have this open source framework called GridOps, which is an implementation of that. And that is actually working right now. So what is in there right now is that you can make a client and a server, and they can communicate through this IAP and IAM. And I will get into a little bit more detail about how these are different in just a moment. And we spent probably 2-3 years just trying to get everything right there and get everything to work in creating a platform for a new asynchronous and more flexible network protocol. And then at that time we realized that it's not so easy to convince people just to play around with infrastructure. We need a use case. And so we decided actually to say, okay, let's focus on this Internet of Data. Let's make that our use case. So that is why we decided to make a desktop application, which will can function as such a client, as a general purpose client for the Internet of Data. And we were talking about that for a while. Should this be a web application or should it not? But seeing that we would risk getting trapped by what is currently possible in the world of the web, we decided to make it a desktop application for now. So this is actually implemented with JavaFX, and for those of you who have not worked with JavaFX, it actually works pretty well, I must say. I was surprised about how easy it is to get an application up and running with that. All these charts that you can see here are actually standard in JavaFX. And we can see that with this project Gluon, it's even possible to get it to run on Android and iOS, so it's a viable alternative. Okay, so we also have some hosted parts, some streams, which are simplified versions of Kafka and stuff like that. This is not so interesting right now. So anyways, what I want to talk about is a little bit this IAP protocol, because that is really that is our suggestion or implementation of what we believe a new protocol could look like if we were to ditch HTTP, and so we can get an asynchronous protocol instead. And let me just start with that. So once we started looking at the internet, like I said earlier, like we looked at HTTP first. Can we use that to reinvent or to create a new platform, a new protocol, a new paradigm of communication, or not a new one, just it's already there, right? Asynchronous communication already exists, but just one that is asynchronous. And at the time we started, there was no HTTP 2, so this was not really possible with HTTP to make it fully, or like easily asynchronous, but also that was one thing we wanted to do. Also, we wanted to make to create a protocol that was designed more around open connections rather than open a connection, send a request, and close it again. Like, you can keep an HTTP connection alive, but HTTP itself, like the semantics in HTTP, is not really designed for open connections. Right? So this is what we wanted to design, a new protocol. We wanted it to be message-oriented, we wanted it to be fast, compact, expressive, and we wanted it to be extensible, meaning that instead of just having or just risking creating yet another protocol which is a one size fits all, we decided that we wanted to have a small base set of principles that it would be based on, and then let it be possible to implement new protocols on top of that. And we wanted it to be routable, easily routable, and we wanted it to be plug and playable. And we believe we have succeeded in that. And let me just have a look at that here. Yeah, so when designing a new protocol, we would like it to be able to support a wider set of protocol communication patterns than what you get with HTTP, or at least before HTTP 2. So some of this is possible now with HTTP 2, but so that's another thing. We might actually at some point switch to HTTP 2 or something like that, but we haven't decided that just yet. But a protocol that needs to fit the Internet of Data definitely needs to be able to support these patterns. The first one, notification or broadcast, is where some transmitter is sending messages out to the world, and anyone who wants to listen can do so. For instance, this could be a digital radio station, right? You're just broadcasting radio messages, and you don't really care who receives them. You're just transmitting that. This is not something that HTTP was designed for. Request response, this is exactly what HTTP was designed for, so there's nothing particularly mystic about that. We wanted also to be able to support multi-request response, meaning that you are sending maybe 5 messages in and you want a single response back, or the opposite, that you send a single request in and you are getting 5 or 10 or whatever responses back. And then a specialization of that we call subscription, which basically means you send a message saying, I would like to subscribe to this stream of data, and then you just receive messages until at some point you say, thank you, I don't want to receive any more messages. I can cancel your subscription. So this is a little bit hard to squeeze into HTTP, at least HTTP 1.1. So that's why we decided to design this IAP protocol. As I said earlier, IAP is message oriented, and messages consist of a single binary block of data, and there's a base in it, and then there's an extension inside each of these messages. The message base consists of 4 fields at this point, which is like kind of standard information, but it just tells who is going to receive this message, the receiver ID, and at this point it's very undefined what exactly a receiver ID is. That depends on your use case. And then it contains a semantic protocol ID and protocol version and a message type. And that means that if you are implementing, or if this is a message that belongs to a specific semantic protocol, for instance, file exchange, then it will say, okay, this is a file exchange protocol in version 1.1 or 25 or whatever version number we have reached. And then it says the message type, and the message type is the exact type of message within a protocol that this message represents. So for instance, in file exchange, it would be download message, or it could be upload message or whatever, and the file and the message type would then be different. Once you have that information up there, once you have the base, you can easily have a completely different looking message extension, which is targeted very specifically at the concrete semantic protocol. So if it's file exchange, the fields down in the message extension can be very narrowly targeted at that. If the protocol is RPC, it can be very narrowly targeted at that. Or if it's just broadcasting data, you can target that. That means that instead of now with HTTP, where we have all of these standard HTTP headers, which are actually semantically tied to a paradigm of document exchange, of sending and receiving files over the internet, we're trying to squeeze them into to represent other things, like you do with REST, right? You can design the protocols that you need very much like completely targeted to the use case. And this, of course, means that the messages can be smaller because you're not carrying a lot of weight from other like protocols. And it also means that we can actually, even though all these protocols are different, because the message encoding on the outside is the same, that means that we can pretty much use the same client and server frameworks, because the delimitation or the delimitation of the message is the same. It's only the fields within the message that are varying. So you could imagine this as being a JSON object. It's not, but it could be a JSON object where the first 4 fields are always the same, and then the rest of the fields in the JSON object would be something that is completely targeted at the protocol. So that is what we have implemented, right? And from this we will be on top of this IAP, we will be implementing a couple of standard semantic protocols, and the semantic protocols are these protocol extensions, the versions of the protocols that are actually doing something. So right now we have a secure channels protocol, which is an adaptation of TLS but running on IAP, like with these message formats, so that it instead of having TLS running at the bottom of your application, where your application cannot actually that easily tap into it, we kind of expose this whole security protocol, so that you can decide how you want to exchange keys, or if you want to pre-share keys, or whatever you want to do when you want to establish secure connectivity. It's not hidden away down at the TLS layer. So that's one thing. We will be defining a directory protocol, because just like there are problems with HTTP, there are problems with DNS as well. If you need to change today, to remap a domain name to a new IP address, as you know, it will take a couple of hours before that is propagated all over the internet. And unless I'm completely mistaken, you can only map a domain name, to an IP address. But what we actually, and that means that we have hardwired, in a way, HTTP and a lot of other protocols to certain port numbers in TCP, because when the only thing you can see is where the service is located, but not on what TCP port it is located, then you kind of have to just assume that it is always located at port 80 or whatever. This is one of the things we want to change, so that when you're mapping a domain name or an ID to an IP address, you're also mapping it to a port, so that we can start using all the ports on our servers. Right? Why should we only be running HTTP on port 80? You can do that, but then if you do that in the web, all of a sudden this little port number bleeds into the URLs, which is very annoying. So these are some of the things that we are working on. We will be defining an RPC protocol, because obviously we need that. But we will also be implementing some variation of that, which is a remote execution protocol, because when the difference between them is that, like, when you're calling, like a standard RPC, you're just calling a service somewhere on a server. You're sending a couple of parameters, and you get a response. With RAP, it's like a remote execution protocol. Means you're sending a script to a remote server. The script is executed on that server, and that script then generates a response to you. This is what you do actually when you are sending an SQL script to a database. This is exactly what you're doing. And we need to get these kind of things, like this kind of more advanced querying, out and have that supported by a protocol directly. So that is what we'll be implementing. We'll be implementing file exchange, because like if you look at what the web is today, it's usually a combination of file exchange and RPC calls. And then we will be implementing some subscription protocols. And these will be general purpose protocols, but if anyone wanted to use to create their own protocol based on IAP, they could easily do that. If you have two services in a tight, like two services running internally doing some kind of financial trading or whatever, and you want them to only send the exact data between them that they need, you can kind of like define your own protocol with only exactly those fields. That way you can get a lot more speed on the protocol and make sure that a lot less data is exchanged, and the less data that is exchanged, the easier it is to pass, and then all of that bleeds into, you have a lot less garbage collection and all that stuff. So this is an advantage on a lot of derived levels. So another requirement we have for a new protocol that can fit the Internet of Data is routability, and that means that messages must be very easy to route for intermediate routers. And one of the issues you have today, if you were to route HTTP, then in order to know where where a message ends, you have to first pass through all the HTTP headers. Then you get to the content length, and then you can kind of see how big the body is. And so we have designed the message format in a different way, so that at the very beginning of the message it says how long the whole message is. It means a router can very easily see that, okay, I know exactly that the next 500 bytes, that is this message, and then I can just send the rest of the next 500 bytes down a different pipeline. So this is something that we have built in. This is actually coming from the message encoding that we have used to implement this protocol, and I will talk a little bit about that now. And this is what we call ION, which is just a short for IAP Object Notation. So ION was designed to be a message format to send messages compactly and across the internet between a sender and a receiver. And it was designed specifically for use with IAP, but it can be used also outside of network communication. It's designed as a general purpose data format, so you could also just you could write ordinary data to it. And it is supposed to, or it was a requirement that you can support a lot of common use cases well, like for instance, when communicating over the internet, you often need to send binary data, and HTTP can do that, but today we're using JSON a lot when we are encoding more advanced objects, and JSON is not very good at encoding binary data, right? You would have to encode it as a base 64 included in your JSON data, and then it will take up 1/3 more data than the original binary data does. JSON also has a couple of challenges when it comes to compact representation of numbers and dates. And so we have created fields in this iron that are very compact representations of that. We have, of course, the typical key value pairs, like a JSON object. You have a property and a value. And these objects can be hierarchical, just like in JSON can be. Then we decided to build in, we have support for arrays as well, naturally, but then we decided to build in something which is something that you also don't see in JSON, when you can maybe model it, but it's not there, like the support for tabular data. This is just like a CSV file, where you're sending like column names one time, and then you have a lot of rows after that, just with the data, and you know that the value at column 5, that's the value in dollars or whatever. When we look at communication between clients and services, especially when it comes to data, a lot of the data that is exchanged is tabular data. Like you're sending a request to a server and you get 10 results back. Like most of these 10 results will contain exactly the same fields. So there's no reason to repeat the field name for every one of these 10 results. So that's what we did with this tabular data, that you can actually just include the field name once and then just the rows of all the values there. So that actually works very well, and when you are compressing, or like we have already measured that you save a lot of data, and you thereby you increase the processing speed quite a lot, having fields like that. And we have a couple of more requirements here that we wanted to be compact, that we have already achieved, and then fast to read and write. And in any case, when there was whenever we had to make any choices between read and write speed, we favored read speed, because data is typically read a lot more than it is written, especially if you read from disk. Okay, so now it's getting it starts to get a little bit technical, a little bit more technical, and this is I'll get into the basic encoding of iron. But if we do not get through it all, that is not really super important. But let me just run through a couple of these slides, and I think we are close to being out of time. I just want to go through 2 of them, and then we can have a couple of questions. The basic encoding of an iron field is that it is a TLLV format, which means that a field of data contains a type, then it contains a length, and then a length, and then a value. And here I have it. I've just shortened it as type, length, value. And when you look at the bytes up here, like this is an example of a field, you can see that there's a lead byte, and the lead byte consists of 4 bits that are telling what kind of field type it is. And the field types, if I go back one slide, that is this, whether it's a field of binary data, whether this is a number, whether this is a string or a calendar, like a UTC time, or if this is a table of data or whatever this is, right? So that's the field type, and then we have a number of length bytes, right? That is telling this next 4 bits. They are telling how many bytes are used to represent the length of the field, not the field itself, not the field length itself. And so that basically means that we can have variable length fields instead of always using 4 bytes to tell how long the value of the field is. We can, using these 4 bits, say, well, we are only using it's a short field, so we only need 1 byte to describe the length of the field. That means we can get very compressed fields, which is very nice when we are encoding, for instance, integers or whatever. This is like the basic format, right? And this means that the format is self-describing. If I've been asked a lot of times, why did we not just standardize on something like protobuf? And the thing is, like we had a requirement that the data format has to be rootable. For a data format to be rootable, it has to be self-describing. It means that somebody who does not have the schema in protobuf, you need a schema in order to pass the protobuf message. And so someone sitting in between sender and receiver that does not know this schema cannot actually see when the message starts and ends. So you need some kind of self-describing mechanism inside the data. So that's what we have implemented this way. You can always, whenever you see an iron field, you can look at the lead byte, you can see the field type, and you can see exactly how many bytes that field takes up. So there we have already met 2 of the goals of being self-describing and thereby rootable. And this also means that because we have the variable length of the length fields, means where we can make very compact representations of data. And this is actually, turns out these kind of fields are very, very fast to read and write compared to like serializing to and from JSON and from data. And it's also reasonably easy to allocate memory for. Like one of the challenges when you're designing a platform, like you get a message in, and you need to allocate some kind of memory, like once you start getting the data in. And you may not know, if you do not know ahead of time how much data you're getting in, it's just a JSON object. You do not know as a server how much data should you allocate for that message. But this way, you know already when you receive the iron field in the beginning, you know exactly how much memory to allocate for it when you receive it. Okay, there are a lot more details here. I just want to say very quickly that you can actually nest these fields inside each other. So you can have, like you can see up here, the top one is a big field, and inside that it has another 2 fields, and inside the second of the 2 fields it has another field. So this is how we achieve the ability to model data, which is similar to JSON, where you have objects inside objects and tables and so forth. And so this way you can have nested fields as hierarchies. And once we take the step back to IAP, such a message consists of an iron object, which is a field of key value type or key value fields, and then so there's a key field, and then there's some bytes, key field bytes, key field bytes. These are all like the outer object, the iron object. That is an iron field, and each of these fields inside, these are also these very compact iron fields, right? So the message space you can see is constructed like that, and then the extension depends on the protocol. And I think we will skip the memory allocation part. I just want to say that it might seem a little bit, I don't know, overkill or whatever, like when you're designing a new protocol, that you go all the way down to the data formats and try to standardize that. But once you actually start looking at it, you realize that the data format actually has a lot of impact also on the design of your platform, like on your server platform or client server platform or whatever. And so, yeah, we actually felt with the need to actually go down there and say, if we need a new internet, we need to go all the way down, or not a new internet, but like at least something that fits with the Internet of Data. Then we need to go all the way down to protocols, data formats, everything, analyze everything from the bottom up. And that's what we did. We have compared it to other popular data formats, and we can see like with message pack and SIBO are very similar in the type of encoding. And so we have also benchmarked them and see that like when we serialize to these formats that we get about the same amount of bytes, and the serialization speed and everything is also okay.
Take some questions.
Yeah, I think it's fine now to, I don't have anything more to say. Yeah, okay, so let's just say that was it. The internet is definitely changing, and I think a lot of things will happen outside of the world of enterprise integration and the web where we are traditionally working, and I think we need to keep our eyes open for it and have a look at it. Yeah. Okay.
Yes.
Let's
maybe
take
someone
you
sitting with
person.
the question about what is really going on here and want some have a question. Yeah.
This is quite ambitious, I think. What's the future of this, and how are you found?
This is very ambitious. We also, if I go back here, we realized that, and that is why, like in the beginning, we just had the little corner in the little green corner here, right? Or like we only had the bottom here. So we had the open source.
How you're funding it?
For now, by consulting, right? But yeah, no, we realized that this is very ambitious, and so we needed to kind of like narrow it down and say let's focus on one use case, and that is why we said this Internet of Data, like this data analysis, this is where we can see that is maybe not so well supported by the tools out there today, and also where kind of like the protocols and the technology underneath it focus, and then we hope to kind of build maybe a business around that. That's why we went up there. So, and we will see. For now, it is proprietary. We want these protocols here to be open. I mean, these are openly described everywhere, and like we have the open source toolkit, but it's a little bit of mess. It's in it works kind of state, but we need to clean it up a little bit. And so we are kind of ready to engage with people who are interested in this.
Why don't you ICO?
We have talked about that. There are kind of some legislative problems around that, right? Like we would have to create a utility coin. If we just issue a coin, which is an investment, then we would get a problem with the SEC in the US and things like that. Yeah.
One other question. GitHub, do you have a GitHub account where people can contribute to? Or?
We have a GitHub repository, but I mean, it's not at this time so fantastically pretty, the code and everything, because we have been trying a lot of things out, and some of the things worked, some of them did not work, but some of the things that did not work are still in the repository. So to look at that, I think the easiest way is like would be to find us, find that part of it via this website here, which is kind of like the website for this project, and from there on we link to all these other things, right? We'll kind of clean it up and everything.